Hello everyone, this is Professor Ma and this is the introductions on the sections to green theorems. So let's start out with the line integral works. So we have a vector field F which represent the force at different points at a different force vector is given by two components. The little f is I component and little g is the j components of the vectors. And I have a curve in the planes, and the curves is defined parameterized by some x component xt yt, and the t goes from a to b, and on the plane, and the curve starts from the point p at t equal to a to at time t equal to b, stop at q. Then the total amount of work for these displacements from one P to Q is the total amount of work was given by these dot product formulas. We write as W as F dot with the derivative of the curve C of T. And we also write simply as W is equal to F dot dc, where dc, of course, is the differential notation. It's dc is c point dt. And what does a Green theorem says? Well, Green theorem says if this is a loop, that is the point P and point Q are the same point and provide some conditions. And then this line integral can be converted into a double integral. Double integral over what? Over the region that's enclosed by the loop. Okay, so we start out with be more specific. What I mean by a closed curve is a loop. Here's a curve not closed. The beginning and the end points are not the same. So, and here is a close, but wind up the beginning and the end at the same location, but it intersects itself. So this is not simple. And so closed and simple curves look like this. Basically, if you looks like a circle, okay. And a piecewise smooth curve is, or simply a piecewise simple and close means I can have some specific locations, finitely many places where the points are not differentiable. So in other words, they come in P, the boundary comes in differentiable pieces like these ones. So Green theorems apply to curves of these types, a loop of these types. Okay. And here is another, before we state the Green's theorems, there's another notation which we're going to pick up because we're going to state the Green theorem in this notation. That is the line integral notations. So if I write everything in terms of t, the integral in terms of dt, that I can break up the integral into two components. Okay, one is the ith component of the vector field action with xt, and the y component, the j component of the vector field working on the point, the y component on the of the point on the curve. Okay, there are two separate parts. We wrote it like this. Okay, when you do the dot product, then it comes out to be the f. Okay, so it comes out to be, remember, f is the x component over here, and it's related to these, and then the j component is related to the y, and it's that part. That are two separate component work, if you like. Okay, and we're going to state the Green theorems using these notations. Notice in this vector field, little f, little g can be any real functions I have. So we're going to start out with any two real functions, f and g, okay? And imagine they are the two I and j component of a vector field. So this is how we're going to state it, okay? So a simply connected piecewise loop, closed curve, it's like this. And then the Green's theorem says, suppose I have a vector field over the plane, and I want to compute the amount of works done of a point goes around this boundary C, total amount of work that's being done by the vector field. Okay. And in particular, think of a vector field as f and g as two real functions of the I and j component of the vector field. And then these computations, f dx, g dy, this is w dot dc, okay? This was the integral of c w dot dc, the total amount of works. And it's converted into that. And that's a double integral over the region inside. Okay, and that is a unexpected result, because one side we're doing these line integral pieces of dt's, and somehow it winds up in dA, of course, on the right hand side. So area differential is dx dy. So this is unexpected conversions. Okay. So we convert line integral of vector fields over a C, a loop, into a double integral over enclosed area. So here is example. I have a vector field xy to x, and going around counterclockwise around this boundary of the triangle is the C, okay? And we're going to convert that into integral inside the little triangular area as double integral. And that's very straightforward. So this is the work being done, and Green's theorem says, or take the partial derivatives of the y, basically the y component, take the partial derivative with respect to x, and x component, take the partial derivative to y, and just subtract. And voila. So, and this is what it is as a double integral over the triangle. And it's the same answer as the line integral. Okay. So in this case, we simplify the computations. Here's another example. Okay. Here's an example that after we realize we can calculate the line integral in terms of area integral, then since the area is a circle, so we're going to change everything to polar coordinates. Okay, so we have a point travel around the unit circle back to itself counterclockwise, and it's the same vector field. Now ask what's the amount of work done, and then by Green's theorem says, well, it's going to be the difference in the partial derivative integrate over this circle. Okay. But then this circle is easier if we integrate over this as polar coordinates. So this is what in polar form. X is r cosine theta, right? And then dA, the differential dA is changing to r dr d theta. Okay. And then these can be integrated easily. And that's Green's theorems. Oh, one thing about Green's theorems. If our field is conservative, okay? If our field is conservative, then this is zero. In fact, that's definitions. I mean, well, that's a check for we have if a field is conservative or not. We check the difference in the mixed partials for conservative fields for nice coming from a nice potential. The two mixed partial x y y x should be the same, so the difference is zero. This difference is the mixed partial. So for conservative fields, then this will be zero. Then we have the theorems basically says around conservative fields is path around the loop is zero, or that is path independent, the equivalent statements. Okay, and that's it. And bye bye.